Firstly, I'd like to greet you all and say thank you very much to my esteemed members and guests. I would also like to thank Dr. Twayer and Dr. Bakhtar for the opportunity to speak, as well as the conference organizers. I'm really pleased to present water quality in hemodialysis clinics. Okay, so to briefly go through the agenda, we'll go through the kinds of dialysis fluids, contamination and consequences, how to obtain necessary dialysis fluid quality within a hemodialysis unit, and then of course the customer's view. Maybe a brief comment quickly in terms of dovetailing with Dr. Miner. Thank you very much for your comments on the water quality aspects. I'm going to obviously extend on that quite some in terms of the presentation that we go through. So in terms of kinds of dialysis fluids, I'm sure you're all very much aware of the types of water quality and water sources that we have, namely groundwater, surface water, well water, and treated water from municipalities. What is very important to note is that in terms of groundwater or water in general, there are many contaminants that we must refer to that are found in water sources, namely deposits of salt, gypsum, nutrients, and metals within the soils that leach in from surface and groundwater. And it's very important to understand what these contaminants are in terms of how we then need to treat water in a hemodialysis setting. There are also many factors that influence the water quality and also water sources. I think it's also very important to mention that the water availability in many countries around the world is very, very stressed. Just to highlight the extreme red areas, you can see that it's probably 40 to 50% of the world is going through massive water stresses. And these can be affected also by seasonal fluctuations, which also directly affect microbial and bacterial contaminations. So if we look at the general water treatment system that is presented on the screen at the moment, it's just a general water treatment system that we can find in many dialysis units. And if I start from left to right, we basically have a raw water inlet system with raw water storage. It's very important to note that the water storage system should be a cascade flow system. What I mean by that is that water enters the water storage containers and leaves directly into the pre-treatment setting, where many contaminants are removed, which actually can be a potential threat to the RO system itself. We then have the distribution system going to all the dialysis machines and also a concentrate preparation system. So what's very important to understand about water is the feed water going into a water treatment system in a dialysis unit is of course the heart of it, but also needs to be a water quality that is drinkable. And from that, we can then work with our water pre-treatment system, which removes mostly particles and contaminants which are harmful for the RO membrane. One could say that you could use an RO system with an RO membrane directly from a raw water feed system, but the risk in that is that you would then go through RO membranes on a very regular basis, and it does definitely pose a risk to dialysis. So we need to treat our water from a raw state or a drinking state to a soft water state. We then pass the water through a RO system, and we'll go briefly into the reverse osmosis process in a short while. We refer to this water as permeate. We then use the permeate to also potentially manufacture concentrates, which could be in the dialysis clinic setting, or they could be the concentrates which you use on a daily basis. From there, we have dialysis fluid, ultra pure dialysis fluid, and substitution fluid. And what's very important to understand is we need to have a set of standards for both microbiological and chemical contaminants. So in terms of drinking water quality, what does regulate that water quality? Well, there are various different standards throughout the world. We have the World Health Organization water standards. In South Africa, we have the South African National Standards for Water. In Kenya, there's the WASREB, the Water Regulation Board, and many other standards in terms of drinking water. However, then we move to a very, very important standard, and that's a standard that is being established over many, many years and has been consolidated into the ISO 23500 range of water and dialysis fluid preparation guideline. ISO 23500 focuses on the chemical quality, and this is to, as I mentioned before, not harm the RO membrane or harm patients through a chemical contamination. In terms of RO water for dialysis or permeate, we also then need to regulate the microbial loads on the patient. In other words, as Dr. Miner mentioned, less than 100 coliform units per milliliter is our limit value, and for endotoxins, 0.25 endotoxins per milliliter. Of course, there are other guidelines in terms of an action level. So we've got two levels of water quality. We've got an action level and an alarm limit. The action level is what would trigger the person monitoring the water system to act before we actually then exceed the alarm limits for bacterial and chemical contamination. We then have ISO 23500-4, which is the standard for preparation of dialysis fluids, which must meet these requirements. And then in terms of the European Pharmacopoeia, less than 0.5 endotoxin milliliters, 0.5 endotoxin units per milliliter in prepared dialysis fluids. We then move to the actual dialysis fluids themselves, which is regulated or controlled by ISO 23500-1 and -5, which then, as already mentioned, has specific bacterial loading limits. We refer to ultra pure dialysate or ultra pure dialysis fluid, and their limits are obviously quite a lot lower, a factor of less than 100 times by 100, so 0.1 coliform units per milliliter. And in terms of endotoxins, 0.03 endotoxins per milliliter. So you can see the regulations are very strict and very stringent. And of course, finally, our substitution solution, which is also again mentioned by Dr. Miner, which is a fantastic and new therapy providing many successes for dialysis patients. And the quality here needs to be sterile and non-pyrogenic. Moving to the next slide. So if we look at a typical RO room or water treatment setup, the heart of the dialysis unit being the RO system, we generally need to break down the reverse osmosis process to understand exactly how the process works. And of course, that eventually leads then into the monitoring of the system. So reverse osmosis is a separation process that uses pressure to force a solvent through a semi-permeable membrane that retains a solute on the one side and allows pure solvent to pass through to the other. Reverse osmosis process uses soft water to press against the synthetic semi-permeable membrane, which is permeable to water molecules, but not for impurities. Soft water is pressed with a certain pressure against the reverse osmosis membrane and thus stimulates the osmotic pressure. Since larger molecules cannot fit through the pore, only now water molecules are pressed through the membrane. And on the other side of the membrane, we then have ultra pure water. So if we look at the typical sizes of RO membrane pores and related to various different other aspects of our environment, the human hair is 100 micron in diameter. The smallest particle visible to the human eye is 50 micron. Smallest bacteria is 0.2 micron. Viruses, or the smallest viruses, are 0.002 micron. And the RO membrane pore size is 0.0001 micron. So as you can see, it's very important to note that the RO membrane is the barrier between pre-treatment and permeate supply. So if our RO membrane is intact and well managed and well maintained, and the integrity of the system is according to specification, we know that we are producing the correct water quality in the system. However, it's also then very important to realize that, as I've mentioned on numerous times, the monitoring of the water treatment system is also an extremely important factor. And to ensure the safety of the system, there should be certain monitoring parameters in place. For example, daily, weekly monitoring, monthly monitoring, and annual monitoring. And this relates to the pre-treatment in daily and weekly monitoring, where we're monitoring chlorine, hardness, pressures, tank volumes, backwash of controllers, and salt levels in the softener, as well as the RO performance. Maybe just a quick comment about chlorine. Chlorine is a very harmful, resulting in the hemolysis of the red blood cells in a dialysis patient, thereby dropping the HB. And this can affect an entire dialysis session. So it's critical, for example, to monitor chlorine before every dialysis session, depending on the type of pre-treatment that you have in place. A double carbon filter would then allow you to, as an example, monitor chlorine before dialysis starts. And it's very important that before dialysis starts, someone of the correct knowledge and training should evaluate the system, prize the release of dialysis based on these daily monitoring parameters. We then have monthly monitoring of the RO system, which relates to TMA, yeast and molds, endotoxins, disinfection of the system, quarterly filter changes, and quarterly partial chemical analysis based on risk elements identified. And then, of course, annual monitoring, where complete system is monitored, full water chemical analysis of the raw water, soft water, as well as the permeate. A disinfection and a sampling plan can be set up for every single system based on the risk of, for example, soft water or permeate, as well as the seasonal fluctuations that can influence those risks. So how do we, or what do we use to do the daily monitoring of water treatment systems? There are commercially available test kits that you can use to monitor chlorine, hardness, in terms of disinfection, iodide, potassium strips, as well as monitoring pH of a system. And as I mentioned before, it's critical to monitor these systems on a daily basis and have these test kits available in a dialysis clinic, water treatment system, to ensure that our patients are dialyzed safely from the word go. So we mentioned ultra pure dialysate before, and dovetailing on Dr. Miner, online HDF. What has been identified over the last 5 to 10 years, possibly even longer, is minimizing the patient's risk of cardiovascular morbidity and mortality. So despite significant improvements in the quality and efficacy of hemodialysis therapies in recent years, CVD remains the leading cause of death for dialysis patients. Today, almost every other dialysis patient dies from cardiovascular complications, and it's very important then to make use of ultra pure dialysate fluid with features on devices such as blood volume monitoring in order to help and minimize cardiovascular disease risk factors and significantly improve the quality and efficacy of hemodialysis therapies. So why ultra pure dialysate fluid? Well, patients treated with ultra pure or ultra filtered dialysis fluid have demonstrated a decrease in serum beta-2 microglobulin concentrations, a decrease in markers of an anti-inflammatory response and oxidant stress, an increase in responsiveness to erythropoietin. In long-term studies, the use of ultra-filters or ultra-filtered dialysis fluids have been associated with a decrease in incidence of beta-2 microglobulin associated with amyloidosis, better preservation of residual renal function, and improved nutritional status, which Dr. Tuahir commented on quite a lot, as well as Dr. Miner. These observations have led to the recommendation that dialysis fluid of a higher microbial quality, so-called ultra-pure dialysis fluid, should be used for routine hemodialysis. The use of hemodialysis machines, therefore, should at least be equipped with one ultrafilter to produce these dialysis fluids free of bacteria and endotoxins. Additionally, in terms of online HDF, for online hemodiafiltration, online prepared sterile and non-pyrogenic fluids is required especially due to the direct infusion of high volumes of fluid into the patient's bloodstream. Therefore, it is of particular importance to ensure that no contaminants with chemical, bacterial, or other contaminants may occur in dialysis fluids. So if we have a look at then the contaminants and consequences of associated with pre-treatment and dialysis water, from a chemical perspective, as mentioned before, with pre-treatment, we're removing certain parameters to protect the integrity of our RO membrane, again, which is the barrier between our water supply system and our patient's dialysis water quality. And then from a dialysis water quality or reverse osmosis system, other contaminants which are in the blue categories. I'm not going to go through each and every single contaminant. I think we'd need a very long time to do that, but what we can mention is a few of them which have specifically been documented with toxicity in dialysis, specifically talking about those in red or orange, aluminium, fluorides, lead, nitrates, nitrites, sulfates, and zinc. But generally, of course, we need to remove or control all contaminants to a very specific level of quality associated with the ISO 23500 water standard. Coming then to the bacteriological contaminants. If we look at total bacteria or plate count, you can typically see the growth on a media to indicate the growth rates and bacteria present in water. What is a very interesting point to mention at this point is that growing bacteria on plate counts can also identify yeast and molds. And by identifying yeast and molds on the same plate count, it can then be determined whether one should or should not, as a diagnostic tool, perform yeast and molds as a diagnostic test rather than on a monthly test. We also then have endotoxins as a contamination. And all of these contaminants left untreated in a water treatment system can lead to a growth of biofilm. So biofilm is there's very fancy words for it, a polysaccharide or a specific structure that occurs within a pipeline distribution system within a water treatment system. But basically what we're looking at is a slime that forms within a pipeline where bacteria adheres to the inner walls of the pipeline. This proliferates and grows and eventually forms a protective mucus around the bacterial growth on the inner lines of the pipes, which then can lead to, after disinfection, a dispersal, which then immediately creates a risk for a patient because those dispersals or break-offs can then go directly into the dialysis machine, and these can then pose an immediate risk from a biological contamination to the patient. So the point I'd like to make at this time is control and prevention is a critical factor here. So if we break down what endotoxins are basically found in the wall lining of a gram-negative bacteria. It's a lipopolysaccharide protein complex. They are often released during the proliferation or lysis or breakdown of the bacteria found within a dialysis water treatment system. And the risk here is that smaller parts may pass a dialyzer membrane and cause reactions to patients, specifically the lipid A string of bacteria or endotoxin. So how do we test for bacteria? How do we test for endotoxins? Well, typically we have laboratories available throughout the world. Of course, there are laboratories in Kenya, South Africa, and neighboring countries which perform these tests. And this is the most common practice, but does have lengthy time delays specifically related to endotoxins. The standard test procedure for a typical plate count is 7 days. However, one can have a preliminary result within 2 to 3 days, which does give one an indication then whether bacteria is proliferating or not. And the other method for testing endotoxins is a portable FDA-approved device where you can actually get your endotoxin results within 15 minutes. These systems are available through various different suppliers. In South Africa, we specifically use the EndoSafe next-gen device, and it is definitely an opportunity worth investigating. So consequences of contamination, I think Dr. Miner mentioned very briefly, but let's go into it in a little bit more detail. The most risky elements in terms of our pre-treatment system are the chlorine, nitrates, calcium, magnesium. And typically what happens here is that, as we mentioned before, the RO membrane is the barrier between pre-treatment as well and the patient or the permeate supply. So thus what happens is the RO membrane will block most of the contaminants, bar chlorine. Chlorine does move through the RO membrane, and that is why it's critical to remove chlorine before the RO membranes through carbon filtration, as an example. And if not, then it damages the RO membranes. And the risk here is that we have passages of substances where these contaminants then can move directly through the RO membrane. A softener is also very important regarding the protection of the RO membrane. If we do not have a softener which removes calcium and magnesium through an ion exchange process, we can then actually block up our membranes, which can result in a rupture of the membrane. From a chemical and microbial contamination risk in dialysis fluids, there are, of course, acute and chronic adverse effects here. When we speak about different contaminants such as nitrates and chlorine, this can cause hemolysis. Bacteria results in a biofilm formation in the system. This can increase, there's an increase then of endotoxin concentration. And an example of this would be after the membrane rupture, thus leading then to sepsis in a dialysis patient. So the focus for both scenarios is a chemical parameter monitoring as well as a microbial parameter monitoring. Clinical consequences of cytokine induction or effects of contamination of a water treatment system. There are, of course, many, many more than just these, just a few to mention. Fever, hypertension, headaches, muscular cramps as an acute reaction. From a chronic perspective, you're looking at carpal tunnel syndrome, amyloidosis, and of course, chronic inflammation. Of course, we can spend probably a day going into the amount of reactions through a patient, but I think let's focus on how we can manage the system and therefore create an online substitution fluid of the correct quality. So if we have a look at a typical dialysis machine, most dialysis machines these days do have a ultra pure bacterial filter in place. And if we look at the fluids that actually come into a dialysis machine, we've got the concentrates as well as the dialysis water with a very specific quality, as we've already identified. The machine that mixes these fluids and results in a standard dialysis fluid, which we would use then for a treatment, typically hemodialysis or hemofiltration, etc. Here we've got also a very specific standard in terms of bacteria limits. And then in terms of creating ultra-pure dialysis fluid, we should then pass our dialysate through an ultra-fine or ultra-pure filter. This results then in a bacterial count of less than 0.1 coliform units per milliliter and 0.03 endotoxin units per milliliter. And the idea behind a ultra-pure filter is that the ultra-pure filter has a property of, let's make a conclusion or statement, 99% rejection or retention of bacteria and endotoxins.
Let's conclude, Ian.
Performing treatments with the various different types of dialysis based on our standardized water quality? And the answer, of course, is no. we can produce any form of dialysis as long as we have the right water quality coming into the systems. And this is again based on ISO 23500 standards. So are we ready for hemodiafiltration yet? Well, we have to fulfill the chemical and microbial ISO standards for hemodialysis. We have to have a validation plan for operating and monitoring and maintaining water treatment systems. And we have to maintain the technology of the production of sterile, non-pyrogenic dialysis fluid. So in terms of demonstrating how we would create ultra-pure dialysate fluid in a dialysis device, we have our dialysate coming through in our green line, which then goes into an ultra-pure filter and then passes through the membrane to directly then to our dialyzer, which then goes through a process, as we all know, in terms of dialysis and purification of blood. We then have a ultra pure filter again after the first ultra filter, but after the first ultra filter, you can typically create ultra pure dialysate, but we then pass it through, in this specific example, through a second device, which then is used as our HDF or substitution pump of fluid then going directly into the bloodstream. So then if we break it down and we have a look at it in terms of the customer's view, if we make an assumption now that we placed a completely new water treatment system at the site of a dialysis clinic or a customer, we can then look at what affects or what is important for the customer to have as a support structure. So the customers have the technical availability, chemical quality, microbial quality, and of course, regulatory compliance in terms of ensuring patient safety. So in terms of identifying the responsibilities in the different systems, it is very important to understand that the operator in the dialysis clinic has a function to monitor the systems. In terms of the design of the water treatment systems, the manufacturer has a responsibility to ensure that these devices are manufactured according to those standards. The impact of ISO is based on a global network, as well as the European standards. And if we identify these standards, there are all the standards that have been set out for dialysis have been concluded and summarized in ISO 23500 standard. So what's important then, moving on to the validation of the system, is there must be a plan in place. We must focus on the whole system over a lifetime of the device in order to ensure the correct quality and meeting the correct standards. The validation and surveillance of the system is very, very important. There's different qualification processes that must be in place for the manufacturer as well as for the user. The surveillance of the system, it is very important to have a surveillance system, as you've mentioned again, to reiterate, daily performance monitoring, and your supplier of your water treatment system can assist you with putting a plan in place for these systems. In terms of validation, it's very important to have the operational data qualification, the microbial qualifications in place, as well as our chemical qualification processes in place. And then coming to the last and a very important strategy of a water treatment system, as you mentioned before, biofilm is a very clear risk in terms of dialysis contamination after the RO membrane, and biofilms can become resistant to disinfectants. So it's so important to control it before it actually forms. If we have a look at the disinfection strategy of a water treatment system, it must be regular to control bacterial contamination. A disinfection strategy should be preventative rather than reactive. How can we define this from a graphical representation perspective? Biofilm grows over time. If we don't perform disinfections, then we have a steady growth, eventually a logarithmic growth of bacteria above our acceptable levels. However, if we have a standard regular disinfection process in place, for example, monthly, we can then control the proliferation of bacteria and biofilm. And if we have a heat disinfection system in place on a weekly basis, it provides further and more accurate control of bacterial contamination. So it's not so much the technique, but rather the frequency that is very relevant. Our disinfection methods can relate to the RO system, the RO membranes, as well as the ring main. In addition to that, it's also very important to understand the risk on the water inlet circuits of dialysis machines, which are often not disinfected. So it's very important that the future of your disinfection systems does include the piping systems that actually go to the dialysis machine from the ring main or pipeline. So quality control is of paramount importance. Is it complicated? Not really. From your local suppliers, you can get local support in terms of looking after the monitoring of the system. At the moment, the system monitoring is very much related to a manual paperwork system. However, this can be automated through electronic systems which are available from suppliers to standardize documentation and to summarize it and to have it uploaded automatically for a consolidated view through a software system. My last slide then leads to the different structures that are available from your water supplier to assist you with the monitoring of your water treatment system and the planning thereof. And these relate to various different, from basic, advanced to premium support services from a maintenance and monitoring perspective. So we can have a very low level or very high level of support structures that are in place. Thank you very much. If there are any questions at this point in time, I'll be happy to answer them.